Hello again, calculus students. The topic for today is what derivatives tell us. Well, derivatives, it turns out, keep track of some very fine details of a function's behavior, including things like where the function is increasing and decreasing, where the graph of the function is bent upward and where it's bent downward, and where the function has its peaks and troughs. So in today's lesson, we're going to learn how to extract that kind of information from the derivative about a function.
Hello, calculus students. The topic for today is what derivatives tell us. It turns out they tell us quite a lot. Today we're going to talk about what derivatives essentially tell us about the behavior of the graph of the function. The sort of things we'll be seeing is that from the derivative, we can find out where the function is increasing, where it's decreasing. We can find out where it's bent downward and where it's bent upward. And we can also find those special places on the graph where, maybe we find the places where it peaks, the local maxes. And we can also find the local minimums. And we can also find those special places like where the graph changes from bending downward to bending upward and vice versa. So let's get to it. So we'll start with the idea of where the function is either increasing or decreasing. I think rather than jumping straight into a technical definition, I'd like to just look at a picture for a second. So as you scan from left to right on this graph, the places where the function is increasing are just where it's going upward as you scan from left to right. Along this entire interval here, I'm shading in yellow, where up to A, that function is increasing there. And then in between A and B, as you scan from left to right, the function's going down. And so in that interval, we see the function is decreasing. And then at B, it bottoms out, and then it starts moving back upward again. And so it starts to become an increasing function again. And what we're going to want to learn is how to detect where these intervals are. What are the places where it changes from increasing to decreasing and vice versa? So for our technical definition of increasing, we say a function is increasing on the interval if when you take input x1 less than input x2 in that interval and plug them into the function, then you should see that f of x1 is less than f of x2. To see how this plays out on the graph over here, let me pick x1 here in this first yellow interval, and then x1 would be less than x2, let's say is about here. Now plug those into the function, and then the output values you visualize on the y-axis, right? So right about there's f of x1, and plugging x2 into the function, the output's about right there. And indeed you see that f of x1 is less than f of x2, right? And you can do a similar thing if you would pick two inputs in that blue interval where it's decreasing, except you would get the reverse inequality there, right? So the function being decreasing means that when you take an x1 less than x2 in that interval, then the f of x1 would be greater than the f of x2. Now what we want to do is relate these intervals where the function is either increasing or decreasing to the behavior of the derivative. So I've got a copy of this graph down here. Since it's getting a little cluttered, I just want to pick like a representative point. So we had these three intervals, right? And I want to pick some representative points from each of those intervals and look at the derivative. Like for example, if I pick this point here and I look at what's going on with the derivative, well, geometrically, the derivative is the slope of the tangent line. So when you look at this tangent line here, looks like this, and I can see that that slope is positive. So let's call this point C1. I see f prime of C1 is positive. But if I would pick some second point, let's say here, C2, and look at what's going on with the derivative, I see that the derivative is negative there because, I graph that tangent line, it points down and to the right. So here, f prime of c2 appears to be negative. And then if I pick another point over here, let's say c3 in that rightmost interval, and since that line points up and to the right, I can tell that the derivative is again positive. So it looks like, from experimentation, that wherever the derivative is positive, that's where the function's increasing, and wherever the derivative is negative, that's where it's decreasing. And in fact, that's a theorem. Theorem 4.7. Of course, there are some hypotheses that have to be observed. You got to suppose that you got a continuous function on the interval, and it needs to be differentiable on the interior of that interval. So if your function was defined on a closed interval a to b, you need it to be continuous there, but then you need it to be differentiable on the open interval a to b. If you know that the derivative is positive at all the points in that interval, then you know your function is increasing, and you know that if the derivative is negative, then your function's decreasing on that interval. Now maybe we can see why this is true by looking at a proof of it. So we'll start off by supposing what the hypotheses are. Suppose f is continuous on that I and differentiable on the interior of that interval I. And there's really there's two facts to prove here. We're just going to prove the case when the derivative is positive. And then the case that the derivative is negative would be very similar. So if f prime of x is greater than 0 for all x in that interior of the interval I, let's see what we can get going with it. Well, I want to show that it's increasing here, so I need to take an x1 and an x2 in that interior of that interval I, and suppose that the x1 is less than the x2. And what we want to show, WTS want to show, is that f of x1 has got to be less than f of x2, because that's the precise definition of what it means to be increasing. The thing is, we see that f is continuous on this closed interval x1 to x2, which is a subset of that interval I that we started with. And remember at the beginning we said f is continuous on I. So if f is continuous on I, it's certainly continuous on this subinterval. And we see f is differentiable on the open interval x1 to x2, because that's a subset of the interior of I. And we supposed originally that the function was differentiable on the interior of I, so it's certainly differentiable on a subset. Okay, so does this look familiar, where you have a function that's continuous on some closed interval and then differentiable on the open interval? That's the setup you need to use the mean value theorem, and that's exactly what we're going to do. So by the mean value theorem, we know there is some c in the open interval x1 to x2 such that f of x2 minus f of x1 divided by x2 minus x1 is equal to f prime of c. And I just want to point out a few little things about what we got in this equation here. What do we know about f prime of c? At the beginning of this argument, we supposed that f prime of x is greater than 0 for all x's in that interior of that interval I, and so that applies to this f prime of c, so this is positive. And similarly, I can look at the denominator of this fraction. x2 minus x1 is positive just on account of x2 is greater than x1, right? So if you've got a fraction, we know overall the fraction is positive because that fraction is equal to the thing circled in red there, which is positive. And I know the denominator of that fraction is positive. So I can conclude from all that f of x2 minus f of x1 must be positive. And I can rewrite that inequality as f of x1 must be less than f of x2, which is what we needed to show. And then the argument for when the derivative is negative would be exactly the same, except for the part that I've circled in red would be negative, but I would still have positive in the denominator on the right-hand side, so that would force the numerator to be negative, which would force the opposite inequality f of x1 would have to be greater than f of x2. So that's how that proof goes down. So remember I said when we covered the section on the mean value theorem that the mean value theorem was an important underpinning to big results in calculus. Well, this is a very big result in calculus, that the derivative tells you where the function's increasing and decreasing, and it all comes down to using the mean value theorem. Let's do a concrete example. Here's a function, f of x equals x cubed over 3 minus x squared, 5x squared over 2 plus 4x. And I want to find the intervals where the function is increasing and decreasing. Well, if I look at that picture over there, I went ahead and made a graph of this thing ahead of time. It looks like, on the interval to the right of 1, it appears to be increasing. And then on the interval from looks like 1 to 4, it appears to be decreasing. And then it appears to be increasing again once you move past 4. Now, maybe the numbers don't work out to be exactly 1 and 4, but of course, for this first example, we've picked it to work out very nicely. But in general, I can't just look at a graph and get the exact values. I'm going to use this just as a sanity check on the answers that I get algebraically. So let's get the algebraic answer. Well, the intervals where the function is increasing and decreasing are determined by the sign of the derivative. So I need to calculate the derivative, and I would get x squared minus 5x plus 4. One thing to think about, if I want to figure out where the derivative is positive and negative, it makes sense to figure out first, where is the derivative equal to 0, or possibly undefined, because those will be the places where the sign of the derivative will change. Like if something changes from positive to negative, it has to go through 0 in the middle, right? Or possibly there's some sort of weird asymptote going on, and so there could be a place where the function's not differentiable, and then on either side of that, the sign of the derivative changes. So your first job is to find the critical points. I can see that the derivative is always defined, so the only kind of critical points that I need to worry about are where it's equal to 0. And I think I can factor that as x minus 4 times x minus 1. And then solving there, you get x equals 4 and x equals 1, which corresponds to the picture, right? So that's feeling pretty good. Okay, so now we got to check the sign of f prime. So the way we do this is we make a number line. And on that number line, I'm going to make notes about the sign of f prime. Okay, so I'm going to put my two critical points on there. I had x equals 1 and x equals 4. These are places where the sign of the derivative might change. The sign of the derivative can't change anywhere else. In order to change from positive to negative, it has to go through 0 or a place where the derivative is undefined. So all we need to do is plug in some test points. So I'm going to pick a little test value out of each of these intervals. Like maybe I'll plug in 0 as a test point, and 2 as a test point, and 5 as a test point. So in red here are my test points. When I say they're test points, I'm going to plug them into the derivative. So like, what is f prime of 0? F prime of 0, if I plug that into the derivative, I get 0 minus 5 times 0 plus 4. And what I care about is that that's positive. So I'm going to put a plus up here above this interval to indicate that that's where the sign of the derivative is positive. And then I'm going to plug in 2 into the derivative. So f prime of 2, I'm going to get 4 minus 10 plus 4. So that's negative 2. That's less than 0. So in that interval, the derivative is going to be negative. So I'm putting minus signs above the interval 1 to 4. And lastly, I've got f prime of 5 I want to look at. So f prime of 5, I'd get 25 minus 25 plus 4. All I really care about is that that's positive. So if I shade those positive intervals yellow just for visual effect, there's where the function's increasing, and then blue where it's negative, that's where it's decreasing. And so I could state my answer like this. F is increasing on negative infinity up to 1, endpoint not included, together with, so union, 4 to infinity. And I would say f is decreasing on 1 to 4. And we see in that picture up there that our answer corresponds to what we see graphically. It definitely was increasing to the left of 1 and to the right of 4. and decreasing between 1 and 4. In this example, something interesting happens where the sign of the derivative changes. Something interesting can happen at a place where the derivative sign changes. When it changes from positive to negative, that means, that the function's sort of going up and then it starts going down, right? So that's where you find maximums, local maximums. And similarly, when the sign of the derivative is negative and then changes to positive, that means it's going down, and then suddenly it starts moving back up again. And so that's where you're going to find a minimum, right? And that's the content of the next theorem, which is called the first derivative test. The first part of it just says that if your derivative changes sign from positive to negative at a critical point C, then you get a local maximum. And if it's the reverse of that, if the sign of the derivative changes from negative to positive at a critical point C, then you've got a local minimum. And it's also possible that you have a critical point where the derivative just doesn't change sign there. It could be positive on both sides, in which case you don't have a local extremum there. Same thing if it's negative on both sides. So you're looking for places where the sign changes on the derivative. There are some hypotheses in this theorem that you want to pay attention to. You got to assume that your function's continuous on the interval containing the critical point. So that means that we're not looking at a place where there's a asymptote, for example. So the function's continuous at this place where you have a critical point. So that means no jump or break in the graph at that critical point. Now the derivative may be undefined at that critical point, but that just means you might have a corner point or something like that. But we're disallowing any kind of asymptote at this point C. And so we need to assume that our function is differentiable all around that point C, but maybe not at C itself. So that's the sort of thing you would expect to see at a corner point or a cusp or something like that. So that would be okay. We just can't have any asymptotes. So let's look at this function. Well, this is the same exact function that we were looking at in the previous example. Since we already did all the work on it, I thought we should take advantage of it. So in that example, we had this sign chart for the derivative, and applying the first derivative test here would be something like this. Since the sign of f prime changes from positive to negative at x equals 1, we have a local maximum of f of 1, which is equal to 1/3 minus 5/2 plus 4, which is equal to 11/6. And since the sign of f changes from negative to positive at x equals 4, we have a local minimum of f of 4 equals, which works out to 104/3. But the point is, we already had all the work done for where we just had to observe that the derivative was changing sign, and that's how we apply the first derivative test. We just look for those places where the derivative changes signs at a critical point, and the function itself has to be continuous at that point. But we were dealing with a polynomial here, and they're continuous everywhere, so it wasn't a problem. Let's try a different example. So I want to do the same thing here. I want to use the first derivative test, and I want to find all local extrema, and I'm going to use the first derivative test. So first thing I got to do is find the first derivative. So f prime of x, well, let's see. If I use the quotient rule, I'd have e to the x times e to the 2x plus 1 minus e to the x times 2e to the 2x, and that'll be all divided by e to the 2x plus 1. And let's see, I've got e to the 3x. Looks like I end up with negative e to the 3x. Forgot to square the denominator there. And then plus e to the x, all divided by e to the 2x plus 1, quantity squared. Now I want to find the critical points of this function, so I need to figure out where the derivative is either equal to 0 or undefined. But I just observed that derivative is never undefined because the denominator is always positive. And e to the x, its domain is all real numbers, so nothing to worry about here with undefined things. So I need to set that equal to 0, so negative e to the 3x plus e to the x all over e to the 2x plus 1 quantity squared. I set that equal to 0. So after clearing fractions, I'm going to have negative e to the 3x plus e to the x is equal to 0. It might make this look a little easier if we made a substitution. If we let a equal e to the x, then this equation becomes negative a cubed plus a equals 0, which feels a little easier to deal with algebraically. So there I could factor an a out. I'd get a times negative a squared plus 1 equals 0. And then I'd get a times 1 minus a times 1 plus a equals 0. So setting those three factors individually equal to 0, I'd get a equals 0, a equals 1, a equals negative 1. But remember what a is. A is e to the x. So this is e to the x is equal to 0, e to the x equals 1, and e to the x equals negative 1. But I know that the exponential function is always positive. So that means that this first solution and the third solution are impossible. So the only possible one of those equations that makes any sense is the middle one. And then you say, well, for what value of x is e to the x equal to 1? And from there, you arrive at x equals 0 is your only critical point. Okay, so the algebra led me to, there's just this one critical point. So this should make it a little easier to make our, to analyze the sign of the derivative. So let me draw my little number line here. We have put that one critical point on here at 0, and we're going to be analyzing the sign of f prime. Okay, so I need to put in a couple of test points into the derivative. So let me plug in negative 1 and positive 1, seem like reasonable choices. If I plug negative 1 into that derivative, let's see, f prime at negative 1, I'm going to get e to the negative e to the third power, negative third power, plus e to the negative first power over e to the negative 2 plus 1 squared. Well, I know that the denominator is positive, and I can tell that the numerator is positive also because e to the negative 1 is greater than e to the negative 3. So the negative term is less than in magnitude the positive term. So this is going to be positive. And then if I look at f of positive 1, I'm going to get negative e to the third plus e to the 1 all over e squared plus 1 quantity squared. This time it's kind of the reverse. The e to the third term is bigger, and it's negative in the numerator. So I can tell the numerator is negative, and the denominator is always positive. So this is less than 0. See, I didn't need to know the exact numerical value. If you wanted to, you could certainly plug those numbers into the calculator, but I was just using a little number sense to see whether it was positive or negative. Okay, so now I can tell from the sign chart that f is increasing on negative infinity to 0, and I can tell f is decreasing on 0 to infinity. And I can also apply the first derivative test. So by the first derivative test, since the sign is changing from positive to negative there at 0, I can tell it's going up and then it's going down. It's got a maximum there. There's a local maximum of f of 0. And f of 0, I guess, what would f of 0 work out to be? F of 0 would be 1 over 1 plus 1 would be 1/2. 1/2 at x equals 0. We really should maybe go graph this and check our answer. See if our algebraic work matches up with what our analytic work told us. So that original function, e to the x over e to the 2x plus 1. Let me grab a quick graph of that and I'll be right back. Okay, so after popping the graph back into the lecture, we can see it seems to match up. Indeed, the function was increasing to the left of 0, and then it peaked, and then it started going downward there from 0 to infinity. And we can see the first derivative test was right. There was a maximum there at x equals 0, where the y value was 1/2. So cool. This last example points out something that's kind of nice when it happens. It's a special case whenever you just have one local extremum. if you just have one local maximum, it's an absolute maximum. I mean, if there's only one peak and then it goes downward from that on both sides, and the only way it would ever come up again is if there was another place where it bottomed out, then you'd have another critical point, right? So if there's just one critical point and it's a maximum, it's going to be an absolute max. Similarly, if you just have one local min, it's going to be an absolute minimum. And that's what this theorem 4.9 says. Of course, there are some hypotheses. The function has to be continuous on that interval, and it has to contain exactly one local extremum at a critical point. Actually, you don't even have to assume C is a critical point here, but I guess it would kind of have to be. But anyway, yeah. So like that last example that we had, in that previous example, we saw that there was just one local extreme. It was at x equals 0, a local maximum. So f of 0 is an absolute maximum. And that was certainly borne out by the graph. This happens enough that it's, worth making note of. I mean, sometimes you just get one critical point. And so when that happens, you know that if there was a max there, it's global. If there's a min there, it's global. The next topic has to do with concavity and inflection points. Concavity has to do with whether the curve is bent downward or bent upward. So when a curve is bent like this, that's concave up. So happy faces are concave up, and if it's kind of bent down like a sad face, that's concave down. And then, when you have a graph, you've got some areas where it's bent downward and some places where it's bent upward, like you can see in this graph. Now I want to relate where it's concave up or concave down to the derivative. So I want you to watch this progression of the derivative. So I'm going to make a little animation here, and I want you to follow the slope of the tangent line as you move from left to right. That went pretty fast. Why don't we check it out again? So did you see that? Did you see how the derivative was decreasing as the red arrows progressed around that curve where it was bent downward? And then when the curve started to bend upward, where the green arrows are, we see that the derivative was increasing. If we're talking about f prime is decreasing, what we're really talking about here is that f prime's derivative is negative, i.e. f double prime is less than 0. And similarly, if f prime is increasing, that means that f prime is greater than 0. Or in other words, f double prime is positive. So that motivates this definition right here for concavity. Concavity is this. When f prime is increasing, f is concave up. And whenever f prime is decreasing, that's when f is concave down. And then, of course, whenever we say f prime is increasing, that's what we were talking about up there. F prime increasing means f double prime is positive, and then f prime decreasing means f double prime is less than 0. And then they also mention this bit of terminology, inflection point. Inflection point is a place where the function is continuous and it changes concavity, maybe from up to down or vice versa. So for example, here, there was some point where it changed from red decreasing derivatives to green increasing derivatives, somewhere in here. So maybe your inflection point would be about there. So inflection point is where the concavity changes from up to down or vice versa. Okay, so for this example, we'll figure out where that function 2x squared natural log of x minus 11x squared is concave up and down, and we'll figure out what are all of its points of inflection. So we got to calculate the derivative and then the second derivative because this is all based on the sign of the second derivative. So calculate the first derivative and we get 4x natural log of x. And then we'll have 2x squared left alone times 1 over x. That'll just be 2x. And then minus 22x would be the derivative of the 11x squared. And let's go ahead and compute the second derivative. Okay, so we'd get 4 natural log x. And then plus 4. Because you'll have 4x times 1 over x is just 4. And then you've got, well, that's just negative 20x above, so minus 20. So this simplifies out to 4 natural log of x minus 16. Now, if I'm going to figure out where the second derivative is going to be positive and negative, I have to figure out where it changes sign, and it'll change sign where it's equal to 0. So I need to set the second derivative equal to 0 and solve for x. This is where you'll get potential inflection points. So 4 natural log of x minus 16, set that equal to 0, and you'd get natural log of x has to be equal to 4. And natural log of x will be equal to 4 exactly where e to the x, well, x is equal to e to the 4. And e to the 4 is a pretty good sized number. That's like, I don't know, somewhere in the vicinity of 60 maybe. So let's make a little sign chart here and see what's going on around e to the 4. This will work very similarly to what we do with the first derivative test where we check, where the first derivative is positive and negative. But here we're doing where the second derivative, we're going to check the sign of our f double prime, which was 4 natural log of x minus 16. And we have this one potential inflection point of e to the 4. And also remember, since that original function involves natural log, the domain is 0 to infinity, so we can't have any negative values in there. So my number line really starts at 0 and goes to the right, 0 not included. So I need to put some test points in here so I can check the signs of things. So maybe I'll put, I don't know, how about e to the 1 and e to the 5 as test points. Those are easy numbers to plug into the natural log because when you plug in e to the 1 to natural log, you get 1. When you plug in e to the 5 to the natural log, you get 5. So if I plug in e to the 1, I'm going to get 4 minus 16. That's negative. And when I plug in e to the 5, I'm going to get 4 times 5 is 20 minus 16, so that's positive. So from this sign chart, I can see a few things. I can tell f is concave up on e to the 4 to infinity. I can tell f is concave down on 0 to e to the 4. And I can tell that there's an inflection point, e to the 4, f of e to the 4, and that number right there, when you punch it into a calculator, you get this pretty big number right here, like negative 8,942.87, yada yada. Let's see what's going on the graph. Let me go graph it and then paste it in here into the notes so we can have a look at it. Okay, so there's the graph. I was a little concerned because I wasn't sure if those numbers seemed really plausible. They seem too big, but it looks like the graph is confirming what our analysis turned out. So e to the 4, if we punch e to the 4 into the calculator, e to the 4 is about 54.6. And so on this graph, this inflection point is somewhere in this vicinity. So this is the point, e to the 4, and then f of e to the 4, which, we punched that in a calculator and we got like close to negative 9,000, and you can see that's about what it works out to on this graph over here. And that's where, so between 0 and that point, the function is bent down, and you can see like this portion of the graph here that I'm highlighting in yellow, it's concave downward there, right? And then the sign changes on the second derivative, and all of a sudden it's bent upward over here. So here it's got the smiley face, concave up thing, and it does that forever. It's bent upward the rest of the way out. And then this was your point of inflection. When I first graphed this thing, it didn't look like this. So this is something that is a little bit of a word of warning about becoming over-reliant on calculators. If you're not really good at using the technology, it can really throw you off. Here's what the graph looks like when you just first punch it in, and then the screen is sort of set to a standard size window from -10 to +10 on both axes. Well, if you just start zooming out, by the time you zoom out so that you can see everything, it's like all the detail's gone. It's really hard to see what's going on. And so you have to know how to change the size of the window and like start stretching the axes appropriately, like so, to start getting to a window that you can make some sense out of. So anyway, just be careful as you're using these graphers to use them well. Okay, so there's concavity. And just like there was a first derivative test, there's this that would check for local minimums and maximums. There's a second derivative test. So here's how the second derivative test works. So suppose you got an interval where the second derivative is negative. Okay? And you also inside that interval where the second derivative is negative, which means that the curve is concave downward, right? But if inside that interval you got a critical point, so that's a place where the derivative is equal to 0. So if you have both of those, then what's got to be going on at that point C? Well, it looks pretty evident from the picture that if it's a critical point and it's a place where the curve is bent downward, then that tells you that you've got to have a local maximum at C. And similarly, over here, if you have an interval where the second derivative is positive, that means the curve is concave upward there, so it's bent upward. And you know that you got a critical point there inside that interval, then it's pretty clear what's got to be happening there. If it's a place where the derivative goes flat, in other words, the derivative is equal to 0, and the curve is bent upward there, then you've got to be having a local minimum at C. And that's exactly what the second derivative test says. There's some hypotheses you got to pay attention to. You got to suppose that your second derivative is continuous on an open interval containing C, and it's not just any old critical point. It's the kind of critical point where the derivative is equal to 0. But if those hypotheses are satisfied, then just like I said above, if that second derivative is positive, in other words, the curve is bending upward, then you've got a local minimum there. And if the second derivative is negative, then you've got a local maximum at that point. If the second derivative is equal to 0 at that point, then you don't know. The test is inconclusive. You might have a maximum, you might have a minimum, or you might not have either. The thing about this, though, is that all you have to do is plug C, your critical point, into the second derivative. You don't have to check the whole interval necessarily. Just checking it at that point is sufficient. So this gives you a way, instead of having to do like a sign chart, you just have to plug one number. You just have to plug your critical point into this function and then just see if it's positive or negative. So it's a little bit more, like you don't have to look for a sign change or something like that. Okay, so here's a function that we worked with previously. X cubed over 3 minus 5x squared over 2 plus 4x. So we previously calculated critical points. So on this function we had critical points x equals 1 and 4. And f prime was equal to 0 at these points. So if I want to check whether there's a maximum or a minimum occurring at these points, all I got to do, according to the second derivative test, is calculate the second derivative first. So f prime is x squared minus 5x plus 4. And then f double prime is 2x minus 5. So we're just going to plug the critical points, x equals 1 and x equals 4, into the second derivative and see what the sign is. And the second derivative test will tell us whether we're having local mins or maxes at those points. So first we'll do f double prime evaluated at x equals 1, the first critical point. And when you plug that 1 into the second derivative, you get 2 minus 5 is negative 3, and that's less than 0. So what does the second derivative test tell you there? It tells you that you have a local maximum at x equals 1. And when you plug the other critical point, 4, into the second derivative, let's see, you get 2 times 4, 8 minus 5 is positive 3, and that's greater than 0. So we see that we got a local minimum occurring at x equals 4. So you see how easy it is to use the second derivative test. You don't have to make a sign chart. You just plug the number in, the critical point itself, and just see what the sign is, and that tells you whether you got a local min or a local max. It's possible that you'll get 0 when you plug your critical point into the second derivative. And in that case, the second derivative test doesn't really work. You have to try something else, like maybe go back to the first derivative test. All right, so I want to do one last example, and it'll bring a lot of what we've learned together. So I kind of want to throw everything along with the kitchen sink at this example. So we've done 4 things so far, basically. I think about 4 things. So we did intervals where f is increasing and decreasing. We did first derivative test. So that tells you whether you have local mins and local maxes at some point. And then we had concavity, which we could investigate using the second derivative, and inflection points. And then we had the second derivative test for checking whether our critical points were minimums or maximums. The first derivative test and the second derivative test are answering the same question. Do you have local mins and maxes at points? The second derivative test is usually easier to use when it works, but sometimes it doesn't work. But I'm just going to do all of it and just kind of see what happens. Now, I went ahead and graphed the function here. You can see it's got kind of an interesting looking graph. You can kind of see that it looks like something interesting is happening at x equals -3. It's a little harder to tell what's going on the right side of the graph if there's any kind of maximum there. I zoomed in on the graph a lot, and I couldn't really tell even when I zoomed in a lot. So I think it just kind of flattens out momentarily over on the right side of the graph and then keeps on going up. And it appears that there's an absolute maximum there absolute minimum at -3, but it looks like there are no absolute maximums, only an absolute minimum, and I don't see any other local extrema either. So I'm kind of guessing we're only going to get one local extrema, and it's going to be a minimum. Okay, so let's see what we got. Let's go ahead and calculate the first couple derivatives. Because the function is polynomial and all the derivatives are polynomials, I'm not going to get any critical points where the first derivative is undefined, so all I got to do is set the derivative equal to 0 and solve for x. And as I look at that, I don't see any obvious way to factor it, like maybe factor by grouping or anything. But I do see from the graph that it looks like the derivative is going to be 0 at x equals -3. So from that hint, I'm going to divide x plus 3 into this x cubed minus 5x squared minus 8x plus 48 and see if it divides evenly. Okay, so I can see by doing polynomial division that polynomial factors like this, and then I can do the Pythagorean theorem to see if that x squared minus 8x plus 16 gives us anything else, any other zeros. So to get 8 plus or minus the square root of 64 minus 4 times 16. Oh, I guess that does factor nicely. Oh yeah, 4 and 4. Okay, so x minus 4 squared. Okay, so then I can see that x equals -3 and x equals +4 critical points. So I'll make a number line and run the first derivative test. Well, with the number line, I can get both the intervals where it's increasing and decreasing, and I can tell whether I've got local mins or maxes going on. So here we're checking the sign of f prime. Okay, so I've got -3 and 4 are the places where the sign might change. Okay, so if I start plugging test points into the derivative, say -4 and +5 for test points, the easiest place to plug the test points into will be where I've got the derivative factored. Makes it easy to see what the sign would be. Like here, if I plug in -4, I'm going to get -1 times something positive. So this will be negative here. And then if I plug 0 in there, I'm going to get positive times positive. So it's positive there. And if I plug 5 in there, I'm going to get positive times positive. So it's positive here too. Aha, notice that the sign didn't change at x equals 4. I think we can see that graphically. That was happening here. Yeah, the graph was going up and it kind of flattened out for a second and then it kept on going up. So, okay, this is good. My algebra's matching the graph. Always feel good when that happens. Okay, and so then we see it's increasing on -3 to 4 union 4 to infinity. It's not increasing at 4 itself because that's the place where it momentarily flattened out. And then it's decreasing on negative infinity to negative 3, according to my sign chart there. Next, I'm going to look at the second derivative, and I need to set it equal to 0 and figure out its sign chart so I can see where it's concave up and down. So first thing I'm going to have to do, though, is set it equal to 0 and solve for x. Let's see, does that factor at all? 3x, x, let's see, 4, 2, yeah, I think maybe it will. Go 4 here and 2 here, minus plus. Right. And so f double prime equals 0 at x equals, from that first factor, 3x plus 2, set that equal to 0, you get negative 2/3, and then x equals 4. So we're going to make a sign chart for the second derivative. Let me put these two locations on this number line. So there's 4 and negative 2/3. And then I will put some test points in. So I might plug in like negative 1, 0, and 5. And I'm going to plug them into the second derivative, but I'll plug it in here where the second derivative is already factored. So if I plug in negative 1 there, I get negative times negative is positive. So it should be concave up until you get to 2/3. If you plug in 0, you get positive times negative. So it's going to be negative here. If you plug in 5, it's going to be positive times positive. So according to my arithmetic, it should be concave upward on negative infinity up to negative 2/3 union 4 to infinity. And then it should be concave down on negative 2/3 to 4. Let's see if that matches up with what we see on the graph. Oh, and by the way, you can see the inflection points here. We got an inflection point at negative 2/3, and then f of 2/3, negative 2/3, whatever that works out to be. And we got an inflection point at 4 because the sign changed there too. So let's go up here and see what it says on the graph here. So at negative 2/3. So it's saying, our arithmetic is saying that somewhere about here, this looks reasonable, somewhere about there we got an inflection point. And then also at 4, we got an inflection point. And it was supposed to be concave up first, and then it was concave down for a little while, and then it was concave up again. Yep, that looks exactly like what's going on. And we are running out of room rapidly, but we had those two critical points. We could plug, our critical points were negative 3 and 4. So if we did f double prime of negative 3, if I plug negative 3 into the second derivative, it's going to be positive. And so that tells me I have a local min at x equals negative 3. And f double prime at 4, if we plug that into the second derivative, notice you get 0. That tells us it's inconclusive. And this is in terms of the second derivative test. And that corresponds to what we see on the graph too, because actually you don't have a maximum or a minimum there. All you have is just like some place where the graph flattens out a little bit. So, yeah. So you'll definitely want to go back through my arithmetic on this one and flesh it out and make sure that I'm doing it right. But yeah, you see how with these 4 ideas, figuring out where it's increasing and decreasing, with using the first derivative test or the second derivative test or some combination thereof to figure out what's happening at the critical points, whether you have minimums and maximums. And you can check for concavity. If you put all that information together, you can get a pretty good idea of what the graph looks like, even if you don't have a grapher. Just by hand, you can get a pretty good idea of what that graph is. And that's something we'll be doing in our next lesson. So for now, I'm going to go ahead and stop and tell you goodbye. So goodbye.